guys, welcome back to another episode of Introduction to Computer Networks. This is Polly streaming live from NTU again. Alright, hi guys, hi Hongming, Yuan Hao, Yu Jie, hi August. I remember you now. You were attending the lectures last semester already. Yeah, welcome again. And then Zhixiang, Bo Yao, Tasha, Qing Ying, I think, and Neko, and Aslam, and Cassandra. Hi. And Hanjun, okay, I guess you guys would just, pop in. Okay, so I'm just gonna be done with the greetings, and let's go ahead and start with the announcements. Let's see. Yeah, we do have the links for the lectures and the Google Meet session again. And for this week, we have PA1 due on Saturday, all right? And you know what, guys? I saw already 2 teams completing PA1. And one of the teams, I think if I recall correctly, it's Team 4, has completed PA2 as well. Wow. Okay, this semester is going to be exciting. Yeah, hi. And in terms of quizzes, we'll have quiz 4 for sure. Okay. It depends on how fast we can go for the lecture today. Quiz 5 may be due this week or next week. Okay. So I'll update the gentle reminder, the list of assignments due this week after the lecture today. And tomorrow, guys, it's a university holiday, so there will be no lecture. Enjoy the break. Too fast for us. Yeah, I know. No, I don't know exactly. I don't know exactly which team you are, but yeah. So some of you couldn't wait. And you know what? The class is full a little bit earlier than expected. We are actually we are taking more already than we have already planned. Therefore, we couldn't take more, okay? And so that I can release the ad code, okay? And this is a day before the planned release day, all right? So if you see your student ID on the right, take the ad code on the left, okay? So take the ad code to the left of your student ID, and you should be able to use that code to add to this course. Now, we're very sorry if your student ID does not appear, okay, on the list. It's either that you did not quite complete the requirements, for example, completing quiz 1 and 2, for example, not get yourself on the wait list. We're sorry that and also the class is overflow already. Okay, so if you are not on the list, it's either that you did not complete all the requirements or you missed the cut. Okay, so we're sorry that we couldn't accommodate more as I tried to explain it in the first lecture. But you know what? The class is offered every semester because for the exact reason we couldn't take too many students every semester. We couldn't take too many students each semester, so therefore we try to offer the course multiple semesters, so that maximizes the number of students we can accommodate, okay, for the course. All right. Oh, really? I see. So I guess the system is probably too busy because all of you guys are trying to add to the course. So excuse the chaos of the first couple weeks every semester. I guess sort of the trend of how the industry is gonna go, the IT industry is gonna go. can change. And so internet, or for example, AI related courses are just so on demand. And for other disciplines, for example, social science, there will be also subjects that are hot. And therefore, the students would all like to take the courses that talk about these hot subjects, hot topics. So things can get a little bit chaotic, okay, trying to enroll the courses that cover the basics of these hot topics. My suggestion is that stay calm, guys. Allow the university some time, especially the system, the administrative system, the student record system, and the course distribution or course assignment systems. Allow these teams some time to try to fix or update things. All right, so if you are enrolled, congratulations. Okay, if you get the courses you want, hey, you're very lucky. Congratulations. All right, good. Now let's come back to talk about the topics today. So what we'll be talking about today will be in 3 parts. First is access network. We started it last week, but we couldn't finish it yet. So we'll start by talking about the remaining 3 access net technologies. And then the second part is going to be about these communication links that connects the end systems to the core of the internet. Or within the core, you could see that the routers are connecting to each other as well. So communication links. That will be topic 2, physical media. Okay. And then the last topic, that is something that's very different, and we'll be moving. Currently, we are still at the edge of the internet. We'll move to the core of the network, okay, of the internet. So the third part is going to be about the core of the network. And you'll hear that there are generally 2 principles designing a core of a network. All right, good. All right, so first topic, access nets. Last week, right, we introduced 2 access net technologies called DSL and cable. And we took a vote, didn't we? Okay, I asked you guys which one you prefer, right? Because the 2 of them, there seems to be some trade-off, right? DSL offers a lower bandwidth, but that bandwidth is dedicated to a subscriber. Using cable modem to access the internet, the bandwidth promise is higher, but you will need to share that bandwidth with your neighbors, right? So it kind of depends, right? So you guys all took the vote, and yeah, so this is purely subjective. Today I'm going to introduce one more called FTTH, very similar to DSL and cable. These 3 are the most popular access tech for residential access. Okay, and the next 2, Ethernet is the most popular for the institutional network access, and wireless, okay, is for, guess what, mobile access. All right, so let's start from FTTH. But again, for each of these, you want to pay attention to what the amount of bandwidth it offers, and whether it's shared or dedicated to a subscriber. FTTH. Fiber to the home. This is the 3rd access net technology. Unlike the previous 2, where we kind of explore certain existing infrastructure, telephone network or cable TV network, this one here builds its own network. And because the cable are all optic fibers, so it's called a optic network. And it's essentially the internet service providers, if they want to allow users to access internet using FTTH, they will have to go out there and build these optic links into the civil infrastructure. So there are physical contact, okay, through some cables between the central office to home. And so you see in this example, it's very clean. Between the central office to each household, just optic cable, optic cable. The only slight complication and boxes that are a little unfamiliar to you are these. First, optical line terminal. Optical line terminal. So this is a dummy device. What it does is just to collect signal and then convert them into digital bits. Okay, so that these internet data can go on natively through the edge router and out to the internet. Now, what's a little bit more interesting is this box, the optic splitter. We've seen this term, splitter, the third time. Yeah, at the physical level, these splitters are essentially the forwarders or the switchers. Okay, so signals gets forwarded to the right destination at this point. And signal gets multiplexed also so that they can go on further upstream. Okay, so splitter plays the role of demultiplexing signals so that it reaches a particular household, or multiplexing signals so that it goes to the central office. So its role is a little bit like the routers or switches at the core of the internet. So optic splitter here is a very important device for the optical network. In this example, we see there's only one level of it. In practice, there could be multiple levels, so that you could have a regional optical splitter, and then you could have another splitter here inside the building in case there are multiple households in your building, okay, also subscribing to the optical service. Now, these splitters, depending on the mechanism that's running in it, okay, depending on the design, could work differently. Okay, so two typical architecture for these splitters are these, PON and AON. So passive optical network. What it meant is that what's being done here is very straightforward. You just have mirrors so that you can reflect signals so that they go on the right direction to the destination. There's no signal amplification. But if you use active optic network splitter, yeah, these signals get splitted and amplified before they get passed on further. That is very necessary in case there are multiple levels of splitters along the way. As a signal, as it travels longer distance, even though it's optic signal, it still decay. Okay. Now, in FTTH, yeah, the downstream or upstream bandwidth vary, but essentially the maximum capacity is much higher than the cable modem network, than the DSL network. Okay. In Taipei, very typical, you subscribe to services that's downlink 100 megabits per second, uplink 40 megabits per second. Okay. If you have special need, for example, if you are hosting web servers, then you might subscribe to 100 megabits per second downlink and 100 megabits per second uplink as well. Okay, so it can be symmetric, it can also be asymmetric in terms of the bandwidth in going in different directions. So essentially much higher rates, and it really depends on how much you can afford, right? And nowadays, these fibers can also carry telephone or television services. Okay, think about video on demand. So that is to carry TV programs through FTTH. And digital phone, okay, IP phones are one example. The trend is going towards that's just moved to FTTH and then abandon the older legacy technology such as telephone, such as cable TV. So all content, including data, are transmitted over the one and only internet. One ring to rule them all. All right. So what is the bandwidth FTTH offer? It varies, yeah, but much higher than DSL and cable. And FTTH is dedicated, much like DSL. But FTTH is also a lot more expensive than DSL and cable because you need to build the infrastructure from scratch. We kind of touched upon this last week, okay, talking about why cable TV, cable network is cheap. Now, next, institutional network access, Ethernet. Ethernet is also the kind of access technology you use if you are accessing internet from the student dorm, within NTU for sure. The fourth network access technology is Ethernet. Now, this is something that we're very familiar with. All we need to do is to purchase one of these Ethernet switches, connecting our computer through the Ethernet cable to it, and this guy is connected to the edge router. Then data can go out and in from the internet. Such a network access is typically used in companies and universities. okay, as they have direct access to the edge router. For households, we usually don't have access directly to the ISP's edge routers, okay? So even though you're trying to connect your end systems through Ethernet cable to a switch, but that doesn't mean your access network is that Ethernet you're using. Be careful. Now, the rate these Ethernet switch is operating goes from 10 megabits per second 10 years ago all the way to nowadays 10 gigabits per second. But I think typically people use an Ethernet switch at this speed, 1 gigabits per second. And nowadays it's actually dedicated upstream 1 gigabits per second and downstream also 1 gigabits per second. 10 gigabits per second Ethernet is a little bit limited in only those companies who are, for example, hosting a lot of data. Then they need 10 gigabits per second Ethernet, particularly video providers. Yeah, Ethernet. And I was just reading August's comment on chat. Yeah, so hey, 800 gigabits Ethernet these days. Okay, so the standard is just approved. It will probably take some time to have products, okay, under the standard in the market, but you see it's going really fast. All right, and the last one, wireless access. This is the last access technology. It's called the wireless access. That's just how I refer to both of these wireless access technologies in a general term. Okay, the common characteristic is that all the devices, okay, on the same channel will share access. So the way it works is this: devices sending wireless signals. It's picked up by the wireless base station and then passed on to the edge server and then further on to the internet, and vice versa. So these base stations, in the context of Wi-Fi in particular, are also called the access points. Now a little bit more about Wi-Fi. AL2.11b or G, this is actually a pretty old standard. I'm pretty sure that all of us are using AL2.11 at least N. Okay, so that's Wi-Fi generation 4 in another way. The bandwidth with Wi-Fi generation 4 is already close to 400 megabits per second. Okay, and the frequency band is no longer just 2.4 gigahertz, but also the 5 gigahertz band. Okay, that's why when you purchase a new Wi-Fi AP, you see that, hey, a lot of times when you set it up, you see two channels, one for 2.4 gigahertz, the other for the 5 gigahertz. The next major generation is Wi-Fi 6, which operates also on both 2.4 and 5 gigahertz for backward compatibility, in case you're still running AL2.11b or G. For Wi-Fi 6, the bandwidth actually go up this high, 900 and plus megabits per second. Really nice. I think in the next generation, that's called the AL2.11ad. Yeah, for this version of Wi-Fi, it's gonna operate at this frequency band, 60 gigahertz. It's super high frequency, super high data rate. In fact, 5G is also aiming at this frequency. So bandwidth is going to be a lot higher, but you see also that the transmission is very directional, a little bit sensitive to the antenna design, okay, and very sensitive in case there's mobility. All right. Wi-Fi, interesting development there, AL2.11ad. The last one, okay, wide area wireless access actually meant, so 1 megabits per second, this is for 3G, okay. For 4G, we get slightly more than 1, sometimes go a few megabits per second. With 5G, you get easily tens of megabits per second and sometimes very close to 100, but only downlink. I have not yet seen any sort of measurements about 5G uplink bandwidth. It would be very interesting to know if you find any. Okay, but although these bandwidths we're talking about, downlink, uplink, it's increasingly higher and higher even for wireless access. But be very careful. As opposed to Ethernet, as opposed to optic, wireless is, after all, shared access. So these 400, 600, 900, or close to tens of megabits per second bandwidths are shared among all the users. And nowadays, we are probably connected to the network more through wireless access network, okay, than the wired one. Yeah, so I do find myself connecting to the internet through wireless link more now than a wired link. All right, so those are the 5 access net technologies. Wireless comparing to Ethernet, which is wired, offers a lower bandwidth, obviously. And for a wireless network, the air, that space there is definitely shared, okay, by many other wireless technologies, as well as users, okay, that you are sharing a technology with. And the last video here, this is almost more like an example of you see different access technologies being used in a institution or a home setting. Okay, so to sum things up, we've talked about 5 access networks: DSL, cable modem, and the very powerful FTTH, the optical network, to allow all the data, not just text-based, but audio-video data, to traverse. And it's replacing the traditional phone network, replacing the traditional cable TV network. We also talk about Ethernet access and the very, very popular wireless access. Now, all these 5 are access network technologies. These 3 definitely use a lot more for residential access. These 2 definitely use a lot more for institutional and mobile access. But nowadays, in a household, as the demand of using internet is on the rise, and there are a lot more end systems are connected to the internet at home, having just one particular access network to enable multiple machines to go online at the same time is really challenging. So we have a hybrid access network in a way. In this example I'm showing, this is a very typical home setting. Cable modem here is to access to the internet for the household entirely. But after the cable modem, we have what? An Ethernet switch here, okay, which is also called a router, which also runs the firewall functionality. This guy here would allow, for example, these PCs to connect to Ethernet cable to it. Yeah, these PCs are accessing internet using Ethernet switches. And the switch here can also connect to a Wi-Fi AP, and so that these laptops are accessing Ethernet through Wi-Fi. So in just this example, you have devices accessing the internet through different access net technologies. And be a little bit careful when I ask what is the access network for a particular computer. It can be relative, right? So this guy here is through Wi-Fi, this guy here is through Ethernet. But if I ask, how is this household accessing the internet? Yeah, the access network used by the household entirely is the cable modem. All right, so which access tech is being used? It's relative to the questions asked. All right, now let's go on to the second part of the topics today, the physical media. What that means is the cables we use to connect the devices. The first part of the video talks about the basic terms, okay, and the first kind of cable, the Ethernet cable. Right after that, we have the quiz 4 coming up, so pay attention. Here we're going to switch gear a little bit, but still about access network technologies. And so far, if you paid attention, each of these access net technologies operates on some sort of mechanism or protocols. They also operate with assumption on there's a companion physical media. This is important, just like the protocols are important to achieve a certain expected performance, typically achieving a really high bandwidth. Now, so let's go over these physical medias that work side by side with each of these access technologies. Now first, let's define some terms. Bit. These bits are propagated between the transmitter and the receiver. And between the transmitter and the receiver, whatever the media is called a physical link. And these links can be wired. There's a special term called guided media for it. If it's wireless link, then it's unguided media, meaning that the signal might just go propagating omnidirectional everywhere. Okay, as opposed to guided media, there's usually a copper wire or an optic fiber that the signal kind of just follow and being guided to travel through the physical media. There are four kinds of physical medias we'll be talking about. First is twisted pair, and this is one of the commonly used cable for Ethernet. Cat5, this is very old for Ethernet that's 10 years ago. Nowadays, I think we're still using a lot of Cat5 cables, which supports up to 100 megabits per second and might be reasonably okay for 1 gigabit Ethernet. But if you purchase a 10 gigabits per second switch for intensive use, make sure you get these cables, Cat6, particularly 6A. This will allow you to have physical transmission bandwidth up to 10 gigabits per second. Just, by the way, it doesn't make sense to buy a really high-speed switch and the cable limits the speed, okay? All right, so that takes us to quiz 4, right? So, yeah, we just saw Ethernet cable from older version 3 cable to version 5, and nowadays 6A, okay? And I think I begin to see Cat7 cables showing up in the market. So yeah, but more commonly used till today are the 5E, 6, and 6A. Okay? And how they differ is this. First, the modulation frequency, okay? How the bits are modulated, how wide the bandwidth is, the frequency band is. So 100 megahertz, very narrow, okay, and 6A allows 500 megahertz width, okay, to modulate bits. So usually 6A sends data in higher bandwidth. I think you can see it here as well, right? So this is the capacity, okay, 10 and 1, okay, so higher frequency band, higher capacity usually. They differ also in the way they shield these twisted pair cables. So you see in Cat5e, this is just 4 sets of twisted pair cables embedded in one pipeline. So in Cat6, you see that there's something here separating the 4 pairs of twisted pairs, so that prevents some self-interference, okay, between the twisted pairs. And in 6A, you see that each of these twisted pairs have some additional shieldings and individually. Okay. So you can see that the transmission range, effective transmission range, is also towards generation 5 closer. Okay, or 6 versus 6A. 6 only allows up to 55 meters, but in 6A, 100 meters. Okay, and both allows 10 megabits per second. Okay, so generally speaking, wider the frequency band and better shielding it is, higher quality. Okay, now knowing the characteristics of Cat5, 6, and 6A, let me ask you, Q1, consider an enterprise network such as this one above. What cable would you use for link 3 and why? Okay, very important. Tell me why. So link 3 is right here. And link 3 is connecting the 10 gigabit per second switch to the 10 gigabit NAS. Oh, so that's a network storage, okay, that runs on a 10 gigabits per second Ethernet chip. And the distance is actually way longer and wider, okay. So that's beyond 55 meters. Okay, beyond 55 meters. Which one would you use, right? And why? For Q2, this time I ask, what is the cable you want to use for link 5? Link 5, I think, is this one. Oh, it connects to a Wi-Fi AP. And this is a, very old AP, AO2.11n. Okay, so, again, justify the cable you'll be using. Now let's go to the score W2 quiz 4 channel. Let's see. Yeah, again, I guess the question is straightforward, right? Let's see. Yeah, while you guys are typing up, let's see. Team 1 says already 6A for link 3. I always use the best stuff. Well, you know what? That makes sense, isn't it? Because otherwise, if you just used exactly what's good for the device or the system at hand, chances high that you might need to upgrade it again. So if you need to change the cable now, might as well change it to the top of the line. Okay, so that saves labor cost, I guess. All right, so that's a quick answer from Team 1. Let's see. And Nico, could you also add the team number so that the TA and I can take note better whether you completed the quiz. So Q1 for Eneco's team is 6A. So obviously for this particular machine, right, it operates at 10 gigabits per second. So the 5E cable is not good. Okay, obviously it will be underutilizing the capacity of NAS here. Okay, so storing or fetching files from NAS will all be slow. And because the distance is beyond, thank you, Eneco. Wait, are you team 18? Interesting. So distance is longer than 55 meters. Yeah, of course, right? If you use version 6, it works only within 55 meters. But for the Wi-Fi AP connection, because it runs only... Yeah, because the maximum bandwidth offered by the Wi-Fi AP is 600 megabits per second, I guess. So using the 5E, the cheaper cable, okay, should be okay. Oh, okay. If there's no budget constraint, use, the top of the line. I have to say that 6A is significantly more expensive than 5E. So I guess Eneco's team is more budget conscious, right? Boyan here, also budget conscious. Oh, you see that, guys? Two camps, right? One is, hey, let's just go top of the line, okay? The second is, hey, that's just used. That's exactly enough, okay, for the particular setting. Very good. You see, there are two camps. 6A, 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 5E. 6A, 5E. All right, good. So, hey, argue for your choice. Okay, I would say that both will be fine. For smaller companies or companies just starting up, definitely try to be more budget conscious. But for, well-established company, okay, companies having major profit this year, such as NVIDIA, can of course going all the way to the top. All right, good. Thank you for the solutions, and I see that some of the teams are still typing things up, but hey, you guys get the idea. So let's come back to the lecture. So the second video is still about the cables, but this time we'll introduce two more cables. Okay, one is also copper, just like the twisted pair, but the structure of it is different. It's called the coaxial cable. The other is the optic. The material itself is different. It's using the glass fabric. The glass, I think it's called the fabric. Okay, optic fiber. And the last one, okay, it's wireless. Okay, and we in fact call this type of cable radios. Okay, so this video, the rest of the cables you might see. Next in line is coaxial cable, and this picture shows pretty much the structure of such a coaxial cable. What it meant by coaxial is that they have two layers, concentric, and these two layers of coppers allow you to send signals. And because having two layers, it kind of allow the modulator, demodulators to easily cancel out the noises. And so data goes bidirectional on such a cable. A very primitive form of this coaxial cable was used by the legacy Ethernet. Yeah, by baseband, it meant that the bandwidth is really, really small. very low rate transmission, and it doesn't exist anymore. But then cable network picks it up, but enhance it somehow so that they can send multiple video programs over it, allowing multiple channels on the cable. And yeah, the cable exactly used by the cable network is HFC, the hybrid fiber copper cable. Oops. And the third is the fiber cable. Okay, so this is entirely glass-based fiber, and the bits are being sent as pulses. Okay, like that. It works in a very high speed. You can go up to hundreds of gigabits per second. These high-speed fibers are oftentimes used by also the internet backbone, where lots of data are being exchanged. It's also used by the data centers, where there are always high volume data that needs to be stored or retrieved. These fibers, as we heard, FTTH, some of them slightly lower end is used for residential access as well. And they are very high speed, partly because it's very low error rate, because they are more resilient to white noises, background EM noises. The last media is the radio link. This one is very special. It is in fact the one that's used by all wireless and network access technologies. So what's listed here are just a few examples. Terrestrial microwave operating at about 45 megabits per second maximum. Wi-Fi, well, depending on the version, could be lower, 10 megabits per second, or half of 100 megabits per second. Wider area wireless access, 4G, for example, goes up to a few megabits per second. 5G is now tens of megabits per second, okay, with the potential going higher than 100 megabits per second. And satellite radio. Yeah, the bandwidth range spans wider with satellite, probably because of where the satellite is exactly and the technologies being implemented on that satellite. It can go from kilobits per second to 45 megabits per second. But one common feature is this. For satellite links, end-to-end delay will always be much longer than all these other wireless link access. Now, as to exactly how long the end-to-end delay is, it really depends on where the satellite is. For geosynchronous satellites, which sit higher above above Earth, the delay will get longer. The low altitude ones being lower, then shorter end-to-end delay. So, radio links, very special. Essentially, we are sending bits through these electromagnetic waves. There are no physical wires, so it's called unguided media. Data can go bidirectional, well, in fact, all directional, which is a good and a bad thing. If you think about the propagation of these electromagnetic waves, it can be influenced by environmental effects. Having objects around, the objects can obstruct further propagation of the electromagnetic waves. And some objects might reflect, these waves as well, And the waves can be interfering with each other, coming from different sources, or even coming from the same radio source. It's called the multipass effect. So physical media, radio, it's very convenient, but you see the challenge of transmitting signals through these magnetic waves. You see also generally the wireless links, the maximum capacity usually lower than the guided media's capacity. All right, so that's the end of the internet's edge or the network's edge. We now move on to the next big topic. So this is chapter 1.3, the core. Okay, so the first video, not long, only 3 minutes, talks about how it looks like, the core, and the two types of philosophies designing communication within the core, which is what you're seeing, topic 4 and 5, circuit switching and packet switching. As access network is concluded, let's move on to the next component, the network core, which is a mesh of interconnected routers, as I'm trying to highlight here in red color. So you see a bunch of routers very well connected to each other. By well connected, let's see, if you count how many connections this router has to the rest of the internet, 1 here, 2, 3, and 4. 4 connections. Look at this one. How many connections? 1, 2, 3. Look at this one. It's an edge router, all right, but how many connections it has to the rest of the internet? 1, 2, and here, 3, 4. But if you look at a end system, such as this one here, how many connections it has to the internet? Just one here, through the Wi-Fi AP. Look at this PC here, only one. One very clear distinction between these routers to all these end systems is exactly in the connectivity, the number of connections they have to the rest of the internet. For routers, very oftentimes you see more than 2, including 2 connections. For end systems, just 1. And the reason that the routers oftentimes have more connections is because their role are just to transfer data. So it takes us to this very fundamental question. How do we transfer data in such a well-connected mesh network? In general communication network design, very general communication network design, there are 2 major mechanisms. First, circuit switching. Second, packet switching. Idea is quite straightforward. In circuit switching, from the source to the destination, let's build a dedicated circuit, and this circuit is going to be reserved through the entire time of communication, so we could just dump data in, and the performance is guaranteed. And this is the mechanism used by the traditional telephone network. The other technique, packet switching. Instead of allocating resource, creating a dedicated circuit, let's just use the entire link capacity. And let's send data out no matter what. But we cut the data such that it's sent one chunk at a time. And to call such a chunk of data, we have this term called packet. All right, so it's almost like a package, but packet means also a little package. Okay, so we send data in smaller chunks, but use the entire link capacity. Okay. And to tell you ahead of time, internet or the data network is taking this packet switching approach. All right, so that was the overview of the core. Now let's talk more about the circuit switching way. In Polly's opinion, it's easier. All right, now let me elaborate circuit switching a little bit more. This is the familiar network. But this time we see on the network there are 2 circuits. The red circuit connects this end to this other end. Similarly for the blue end. And to establish such a red circuit, which is also called a call sometimes, and the time it takes to set up such a call or such a circuit is also called the call setup time. Okay. And the reason that I need to mention that term is because that takes time, because resource reservation is required going from one end to another, which means this is the first link on the circuit. We need to reserve a certain amount of bandwidth to guarantee that data gets transmitted without any loss or delay. So you reserve link bandwidth for the call. Data is going to go through a switch. This is the first switch. On the switch, memory, CPU, buffer space will also need to be allocated and reserved. So that is what I meant by switch capacity here, to guarantee that the packet will not experience delay and not experiencing any loss. Similarly for the second hop, for the third hop, fourth hop, fifth, sixth, seventh, and eighth. When all 8 hop link bandwidth switch capacity reservations are done, then you build a circuit. But then you see, as Polly was describing, this circuit here, resources are all dedicated. When data are being passed to, no delay, no loss. Really nice. And we call that circuit-like performance. That implies delay and no loss are guaranteed. Low delay, no loss, guaranteed. Similarly, for the blue circuit. And this is really nice because zoom into this segment. This segment here shared by the blue circuit and the red circuit. The two of them, although packet or data will be going through, but these data will not interfere with each other, not incurring delays to each other, and not collide to each other. No packet drops. These days, where we do online meetings a lot, having live YouTube channels a lot, we really like to have this circuit-like performance. This way, we don't have to worry that internet is going to go bad and the live stream is going to break at some point. Nice. Because for certain applications, we do need this type of quality of service. But, you see, establishing the red circuit, we need 8 hops, and each hop takes some time to reserve resource. So there's quite a bit of call setup time involved. This is the downside of circuit switching. Another downside is this. The way we are allocating or reserving resources over the entire path from the two ends of data communication is more. We divide the link bandwidth into smaller pieces. We divide the switch capacity also into smaller pieces. And once we do that, we allocate individual pieces or combinations of pieces to an individual circuit or individual call. But once you do that, if there are no data being sent between the two ends, that piece of resource will then be idle. If you think about it, in a way, it's a waste of resource. If the two of them ask for resource and a call established, but they're sitting doing nothing. So not very good utilization of resource. So this is the second disadvantage of doing circuit switching. Now, speaking on dividing link capacity into pieces, there are multiple ways of doing that. First one is called frequency division, the other time division. This is the second time we see the term FDM. Where did we see this? Yeah, cable modem. We divide cable modem capacity. We divide the cable network link capacity into what? Pieces by the frequency band. This is a very different flavor. Okay, it's dividing the link by the time. Let me illustrate. The example on the top is doing FDM, where we divide the entire frequency band there to 4 users in equal division. So, full frequency band, 1/4 to the blue user, 1/4 to the green user, to the yellow user, and the pink user. TDM works this way. Instead of dividing the frequency dimension, that's divide, okay, in the time dimension. So with these time slots, we allocate the time slots in a rotating fashion to the 4 users like this. Blue, green, yellow, pink, blue, green, yellow, pink. Yeah, it's rhythmic. That is exactly how TDM works. With a good rhythm, with well-synchronized time, the 4 users send data one after another. Very orderly. If we have more than 4 users, how do we do that? You see, we could further refine the division into, for example, 8 parts. That way we can accommodate how many users? 8 users. Similarly for TDM. All right, so that is circuit switching. So you see, the key word is what? Reservation. And that is the reason that the performance can be guaranteed. I have one more video. We have an example as well to calculate how much time to transmit a file over a circuit switch network. That's something that we will do next Tuesday. Okay, but a performance guaranteed. But the downside of doing reservation-based resource allocation is this: idle listening. So in case the resources are reserved for someone else will not be able to use it if the assigned user is not actively using it. Okay, so in terms of utilization of resource, this approach, circuit switching, might not be so good. So it's simpler, but utilization might not be so good. So upside, downside. Another downside is what? There's a call setup time to establish these circuits. Okay, and that's all the time we have today. In fact, this week. Okay, there's not going to be any lecture tomorrow, so I will see you next Tuesday. So, bye. Yes, I'm just gonna edit this to make sure that the list of assignment due is clear. There we go. Okay, bye. Okay, bye. Mm-hmm. Bye. Mm-hmm. Mm-hmm.